Hi, and welcome to part 6 in creating a DLX architecture simulator. In this video, we're going to go over implementing a write-back function, as well as a non-implemented function to read from a file. And this is going to be our way to kind of prepare the state machine and the simulator for when we actually write a program to convert from assembly to binary. So we'll have those functions in place, and we can write a little file in binary and then hopefully import it and execute it. So we're going to write that function today, and it's just going to return dummy values for now to kind of simulate it working. And before we get to those things, we're actually going to start by rewriting our decode function to better handle returning. Because right now, if we open it up, it's kind of hard to tell where to return to. We know we have to return what has to go in the register. We just don't know how to tell which register it has to go into. And because the register destination is different based on which instruction you're using, or instruction type you're using, it's hard to tell where it has to go. It would be nice if they were, both up here and both here or something, so they're both in the right place, but unfortunately they are not, so we will have to handle that. So what we're going to do is we are going to go to our state handler.h, and in our state we are going to add a half word for the registers in use. So we'll use h word registers, and we will put in it's going to be 1 bit for return is 1. It's going to be 5 bits for destination. It's going to be 5 bits for source 1, and it's going to be 5 bits for source 2, which equals 16 bits in total. So this is going to be our way to tell what registers are in use, where the destination is, and what we're if we have to return or not. So the last one is kind of going to always be 1, but there might be a case or two where it comes up not being 1, so we have the extra bit, may as well use it. So we go through and we fetch our instruction, no big deal, and then we go to decode opcode, and we're going to rename it. We'll rename it to decode information. We'll change all these to decode information. And that's just to kind of give it a more accurate name. There's really no benefit to doing it, to changing it, other than just to keep us informed. But so what we're going to want to do is I will leave that there for now. So what we're going to do is we're going to go word response equals decode information, and it takes a word, which is the instruction. So now we'll go down, and we're going to change this to actually returning a word instead of a half word, and up here as well. And now the reason we're returning a full word, we have to declare it up here actually. You can't declare variables inside the case statement. So anyway, so the reason we're returning a word instead of a half word is because we're going to return both the opcode and our registers. And then we're just going to say, okay, take the first half, put it into opcode, take the first half, put it into registers, put the second half into opcode, or the first half into opcode, the second half into registers. But we're going to return them both at the same time. So let's go and define, and we'll name this register info mask, and this is going to be 16 bits. So 1, 2, 3, 4, 5, 6. F, and then define, I'll just name this one opcode info mask, and this one will be the next 16 bits. So that gives us 32 bits in total. No, we need FF, I think, and then, I'm trying to think now, FF, and then, I think that's, yeah, that's right. Well, maybe not actually. Yeah, because 4 bits. 1, 2, 3, 4. Yeah, 4 bits, yeah. So this 4, I can't think now. Why are these so big? Well, let's do half and half then, because that makes more sense. Yeah, because 4 bits is 1 to 15. Yeah, so we would need, yeah, so it is half and half. Yeah, that is, so yeah, it's kind of confusing, but actually it's not confusing at all if you do the math. But so the first half will be for the registers, and the second half will be for the opcode. So we'll do that. So now if we go to decode information, we're going to have to rewrite this. So we'll just go to the top here and start it out. So we are going to need an H word for opcode, and we're going to need an H word for registers. So you can delete this now. Perfect. Alright, so we still have this. So if opcode mask is not 0, it's R type. If opcode mask is 0, or if opcode mask is not 0, it's I or J type. If opcode is 0, or if the first six bits are 0, it's an R type. If the first 6 bits are not 0, it's an I or J type. So that's fine. So that gets us our just gonna clean this up so it's a little bit smaller. So this is gonna get a bit bigger now. So that gets us our opcode. That's great. So now we have, let's create a word response. So we have our opcode, which is great. Now we need to build out our registers. So if opcode is greater than 3, I should just put another thing up here. Define J type max is 3. So I should just opcode. So our J type is either instruction number 2 or instruction number 3. So if this is less than J type max, so if it's less than 3, or if it's greater than 3, that means it's automatically our I type, which means that so let's set this to 0, actually. So the registers equals 0, opcode equals 0. So if opcode is greater than J-type max opcode, that means it's RI, which means we need to and So that means we need to set the leftmost bit of registers. So we have 16 bits, which means we have 1, 2, 3, 4. So we want these to be 0. And this one we want it to be 8. Because so let's create some defines up here. Define set register or set return flag is going to be 2, 3, 4 or 8, like that. So these operate on. Let's move these around. So these are word-based masks. Oops, and these are going to be half word-based masks. So then we're going to need define. Actually, that should be fine. Actually, we can do this a bit differently, actually. So I think we'll try some stuff here. I think if I do this right, I think I should be doing this right if I do it this way. We can say opcode opcode equals 1. So that is no, that's not going to work. Actually, it will be fine. Yeah, it'll be fine. Okay, so opcode equals 1. So let's get rid of, yeah, okay, it's gone. Alright, so opcode equals 1. So now we need to get destination, because that was our first one. Destination, source, and then source 2. Get source 1, get source 2. So now we actually want to do this in here. So we actually want these to be in the braces because they're going to get bigger. The reason we want to do them in here is because I-type and R-type have different. So if opcode is greater than J-type max opcode, then opcode or registers equals 1. And here we want registers equals 1. Alright, so far we have just the rightmost bit set. Okay, so now what we want to do is, we'll start with R-type because it's easiest. We are going to shift registers 5. So that's going to push the leftmost bit, or the rightmost bit, over 5 positions, which gives us enough room for our destination. Or, I mean, our destination. So now you want registers, or, because those will be zeros, so or equals, and then we want, actually we should rearrange these. This should be source 1, source 2, and then destination. Just so it kind of reflects how it actually looks in the instruction. So we're going to want to add some word-based masks. Define register or rs1. Yeah, rs1 instruction mask. So that would be, we would want to skip. We want to skip the first 5. No, in here. we want to skip the first 6 and then get the next 5. So skip 6 would be a 0, and then we want 2, and the next we want 2 gone, which would be minus 12, so 3, and then we would want the next 3 of them, which would be 14, so E, and then the rest are all zeros. So this is 1, 2, 3, 4, 1, 2, 3, or 1, 2, sorry. Yes. I know, 1, 2, let's put this up. 2, so that's 3, and then E is 14, which is 8, and 4 is 12, and 2 is 14, 0, and then the rest are zeros. So that gives us skip the first 6 bits, get the next 6 bits. So we go it or equals I and rs1 inst mask. So what this is going to do is it's going to say get me the value from rs inst mask, which will be, well, now actually I don't know. I don't know if this, let's put a breakpoint here and check this out. I don't know if this is going to return, actually yes, okay, so we do need the trying to think. We're going to need to shift this over, because this will return some massive number, because it's going to give us the 5 bits in there, not the 5 bits we want. Actually, and then we can go registers or equals. So let's remove that for now. Let's go I and rs2 inst mask, and then registers or equals I and rs2 or rsd rd. Sure, let's just go rd1 rd inst mask. So let's go create these now. So define rs2 inst mask, which will be we want the next 5, so 0, 1, because that will be the last bit there, and then the next 4 bits, and then the remaining are 0. And then we want define rd inst mask, which will be all of those zeros, and we want the next 5, so 5, and then 8, because we want the last one, and then there. So that should give us all 3 of our values. So if we put let's put a breakpoint here, and let's try walking through it and see what happens. Make sure we're getting the output we want. Oh, it's a syntax error there. So we forgot to put a dummy variable in there. Alright, so here we are. Alright, so registers is 0. I is a big number. So if we step over, and registers isn't changing. Okay. Oh, it changed now. Because 6, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Alright, let's see. Can I view this in binary? Hey, hexadecimal display, that works. So that's 8. And because it's 2048, it's probably, well, well, actually, decimal, let's look at the binary of that. So the binary is it is how many bits? 1, 2, 3, 4. That would be a half word, right? Yeah, that would be a half word, 4. Okay, so that is, and let's see here. If we were to look at these, so it's only copying over the okay, yes. So what's happening is it's only copying over the last one because we have this will return okay, so let's stop this. Let's go fix it. So the reason that we got 2048 instead of what we wanted was because this is returning a 32-bit value. It's returning a word value. So we need to take this and shift it 16. So I think size of returns. I'm pretty sure size of returns a number of bytes. Yeah, so number of bytes. So if we take size, shift it by size of word times 8. Let's put that in brackets as well. Yeah, because that'll return 2 bytes. Oh, you want H word. Because the shifting needs number of bits to shift. So if we have size of H word, and that's 16 bits, which is 2 bytes, and we times that by 8, so let's return 2 times 8 is 16. So pretty simple math there. So let's do that to all of these now. Size of H word times 8. And then, I wonder if we can do that with this. No, okay. So put brackets around these, and then shift it size of H word times 8. Actually, let's just do a constant. Who cares? This will always be the same, so we shouldn't have to change these ever. So it's kind of a little bit easier to kind of rely on that. So now if we breakpoint this, and we step through, now it should do what we want. So register is 0, it's 40, it's 43. Alright, perfect. Let's look at that. Make sure that's what we want. So if we convert it, we get, so we have here, we have 4, 8. Actually, let's copy that. Let's go above here, paste it, comment it out so it doesn't give us ugly errors. So we have 4, 4, 4, 4. 4, okay. So this is the first half word, and this is the second half word. So 25 to 11, so this is 31. 25 is after the 0, 0, so that. So we have 6, 5, 5, and 5. And these we don't care about. So this is our first instruction. That's our first register. So the reason this didn't work is because this one's wrong. We can't shift this one this much. We have to shift this one by however many bits are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's shift by 11. No, that's not right either, because that's going to put them all at the far right hand corner, which is going to give us the wrong value. So that's actually very wrong. So what we can do is we can say registers equals 1, and then registers shift by 5, and then registers or equals, and then registers shift by 5, and then registers shift by 5. So now what we're doing is we're saying, okay, put 1 in the first one, in the rightmost value, shift it 5, so we get 1, 2, 3, 4, 5, or 5, and then we'll put our opcode there, and then give us, this is basically giving us 5 zeros at the beginning. So it moves everything over and gives us 5 zeros at the beginning. So I wish I could do this in binary, but what we'll do is we'll run this now, let the breakpoint go. Actually, let's stop it and put our breakpoint up one higher. So let's go here. Alright, so start. So let's walk through this. Now what we'll do is we'll open up a converter and look at the hexadecimal as we'll convert the hexadecimal to binary as we're doing this. So registers is 0, okay, so we step over. Registers equals 1. Alright, so we have 1. We don't need to look at that in binary because we know 1 is 1. Okay, so now did we shift 5 already? Oh, it skips the shift 5. Okay, so let's look at 41. Oh, Windows is trying to upgrade my operating system. Perfect. So 41, we get 0, 1, 0, 0. So 1 is shifted over, and we get 0, 0, 0, 0, 0, 1. So this is actually 6 bits, which means we shifted 1 too far. So we need to shift 4 instead of 5. So let's change that, because that's going to not let anything work at all. So let's change this all to 4. So let's try this now. Alright, so step over. Registers equals 1. Alright. So now we get 41 again, which is still wrong. 43. .43 is not correct, okay. So something's not right here. What can we do to test this? So the first thing we want is registers to equal 1, and then we want it to equal 1, 2, 4, 8, 16, 32. We want it to equal 32. So if we shift 5, so that should print out 32. So if we start this up and we find our console window here, so I'll move it to the side so I can easily get it back after skipping here. So registers 1. Okay, I can't keep it on top, can I? No, I can't. Okay, so I'll bring it back in a second here. So shift 5, and then if we print, we're getting 1. So it's not shifting properly. So let's try. I wonder if we have to go registers equals register shift 5. Let's try that. I thought you could do in-place shifting, but maybe you can't. It's 20. Okay. So if we hit the next one, Oh yes, the 20 is, that's hexadecimal, but yeah, it's 30. Okay, so we do have to do that. Okay, so if we stop this now, so we do have to, okay, so there is no in-place shifting. I thought that that would assign or just change the value, but it doesn't. So now if we run this, we're going to stop because we don't have anything to stop us here. Put our breakpoint back in. Okay, so let's try this again now. So step through, step through. So we get 20, which is 1, and then 5 zeros. And this is where our register source 1 will go into. So if we do that, we now get 60. So if we punch in 60, we convert, we get 10,000. So that's, how did that happen? That's a good question. Why would that happen? What is our, let's look at our RS1. It's 1, 2, 3, 4, 5, 6. So if we take this now, these 5, let's keep walking through and see what happens. We get C30 or C03, which is 1100, so it gives us this value here. And then we'll skip again, and we'll add the last one, which makes it 8061. Alright, so now if we look at it, this is one word. So our one word is here. So we get 1, which says, okay, we have, we are returning a value. So then if we go to and we look at the next part, the next part of our instruction is our, oh, I didn't want to close that. So look at DLX sim. So 25 to 21 is register source 1. So we have 6, which is an opcode that says nothing. And then we have 5, which should be RS1, which it isn't. So our next 5 are blank. So something didn't get shifted around properly. So we have to look at why that is. So if we have, let's copy this instruction again. Let's look at what it's doing. So we have 4, 4, 4, 4, 4, 4, and 4. Alright, so we take this value and we'll get, so RS1 mask should be 0, 0, 4. No, that's not right. We want these ones. So these, we'll assume our masks are right, because I feel pretty confident in the masks being right. Actually, we want these. Actually, let's check our masks to make sure they're right, because that could be an error too. So let's go 3E, and then 1, 2, 3, 4, 5. So that gives us 0, 0. So how many is this? This is 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Perfect. Okay, so it's 0, 0, and then so 1, 2, 3, 4, 5, 6, 7. Okay, so this gives us 1, 1, and then 1, 1, 1, which is exactly what we want. Okay, so that's right. Let's check the next one. It should be the next 4. So 1F. which gives us the next 5. Okay, so that's right. And then we'll go with F8, which is the next 5. Okay, so those are right. Our masks are right. So it's something to do with our shifting then. So this would give us the right value. And then we want to, let's break this down into stages to make sure we're doing this right. So let's say word J equals that, and then registers or equals J. So let's see if that makes a difference. So actually, let's go back and let's stop this, and let's see what we're getting for a value after we do that. So okay, so alright, so we get 20, and then we get 60, so we get C00. So let's look at that value. So that gives us this value here. So that's after shifting a second time. Alright, let's look before shifting actually. So let's restart. And let's go through. Alright, so we're at 60. Alright, so 60, which gives us 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. So that means we're 1 too big. Because these 5 are our. So here is the word division. So this is one word. This is a half word. This is a half word. So if we take these 5 are our instruction, or our. So that's how it breaks down here. We have our first register, our next register. We don't care about the rest of that. So what's happening is we're getting this value properly, and then we're shifting at 16, which moves it 16 locations over. So this is 5, 10. So we don't want to actually shift this one 16. We want to shift this one 16 plus 5, so 21. So let's try that. Because what that's going to do is that's going to move it all the way to the right. Or it should. So if we look, now we have 22, which is, now that looks better. That looks more accurate. Alright. So the next one would be 16. So if we skip, so now we have 443, which is 1, and then 5 gives us 2, which is right, and then 5 gives us 3. And then if we go to the next one, we'll get 8861, which is one flag that says, yep, we're returning our first destination, our first source, our second source, and finally our destination. So that's right. Okay. So there we go. So it was a little bit of a misconfiguration there, but so we got it all sorted out. So now if we go to and we do the same thing here, so registers equals 1, and then we'll go registers equals registers shift 5, and then we want from I type, because we don't care about J type, we want register source 1 and then register destination. So register source 1 is going to be register source 1. So we can actually move these out. let's not do that. We'll duplicate this code, I guess, because it's going to affect it. So registers equals registers. I was thinking about a way to try to make that not have to be typed out twice, but we have to because of the fact that we don't want this set always. Actually, no, we can because that's handled somewhere else. So we'll just do registers 1, and then we'll do this, and then paste that here. So this will say, okay, set registers to 1 if we need it to be, and then just start shifting and inserting. And so where's our state handler.h? Let's stop this. Go to state handler.h. So here, this would be R type will be return flag rs1, rs2, rd. I type will be return flag rs1, rd, garbage. And J type will be 0, garbage, or just garbage, because it doesn't even care. Alright, so there we go. So now what we have to do is we have to combine opcode and registers into response. So return response. So we'll say response equals opcode. Response equals response shift it left 16. And then response or equals registers. So that should give us now a combined. So let's go through, make sure that works. So opcode, let's set response to 0 here. Let's start this again. Alright, so response equals 0. Alright, so response equals opcode, which is 20, and then shift 16, which is a big number, and then or equals registers, 8861. There you go. Just like that. So now you've combined them, and return it, done. So now we've gone from getting our opcode, just our opcode, to getting our opcode and the registers in use. So this will also help us in the future if we want to say, check if the registers that we need in this instruction are being used by a different instruction, because they'll be in the state's state's value. So response equals decode information. So now let's go let's create an H word, which is opcode. And actually, we don't need that. We can go in here and go S registers equals response and register info mask, which is going to take the last bits and put it into there. And we can go, this is going to be response and opcode info mask shift left 16. Yeah. So we'll breakpoint there to make sure we get the right value, and make sure that actually this breakpoint up here, make sure it all comes back properly. So, alright. So response is whatever for now. Alright, response. Alright, so our response is, okay, so 2, which is right, and 8861, which is right. So registers is whatever for now, and now registers is 8861, which it should be. So response and I don't think we can actually check this. doesn't tell us what it did there. Okay, so let's just create a hword v, and we'll set v equals response and opcode info mask shift 16. So this is just going to be to kind of check to make sure that this value here is what we want it to be, because we can't really check in the inside of this array index, or inside index in the array, we can't really check if the value is correct. So what we'll do is we'll just put it in a variable to kind of make sure the variable gets the right value. So v is 2. Perfect. Done. Just like that. So it is right. Okay. So now we get the registers and the function all from one value with our decode. So it was a little bit of bit manipulation and stuff, but we got it to work. So now we're going to change our write back, and write back is going to be the value as well as registers. And we don't really need it in execute. We could put it in execute, but we don't need it. Because we get those. Actually, we should put it in execute, so we don't have to do that extra manipulation there. So execute, we'll do hword registers, and then we'll pass registers into the function as well, which means that we're going to have to go to our instruction handler, add hword. We're going to have to go to our jtype, there is none, itype, there is none, custom, we're going to need hword, and rtype, we're going to need to add hword and hword. And then we'll go to here and add hword r for registers, rtype, hword registers, hword registers. That's it's gonna be a bad name. We'll just say regs. We'll call it reg info. So register info. So let's change it in state handler then. And let's go to state handler.c, reg info, just because we already have a value named registers, which is used to actually hold our registers. So we don't want to be getting those mixed up. I mean, this one should be okay because it's inside the struct, but we'll keep it as separate naming to make it simple. So now we can actually delete these. Maybe. Well, first not. So we have 16 bits, and we want these will need to change. So let's go define register define source reg 1 rs1 mask rs2 mask rd mask. Oops. So this is going to be for R type, it's going to be not in here. Where did we put it? Oh, here. So for R type, it's going to be not the first one. So let's make a comment here. So 0, and then 1, 2, 3, 4, 5, and then this one's going to be 0, 5, 1, 2, 3, 4, 5, and then the last one's going to be 0. So that's what we got to make. Oh, wait. These need to be 1s, not 0s. 1, 2, 3, 4, 5. So if we break this down into 4s, we are going to have 0, and then 1, 2, 3, which is 4, 2, 1, so 7. And then we're going to need the rest zeros. Alright, that's not right. So we should break these down into 4s now that we have them laid out. So we laid them out as what they look like in the actual H word, so half word. So what we're going to do now is we're going to switch them into how they'll look in hexadecimal, so we know what to recreate. So that's 12, so C. So this one is 0, and then 3, and then 8 plus 4 plus 2 is 14, so that would be E. And then the last one is going to be 2 zeros, 1, and F. So now we can go rs1 equals reg info and rs1 mask. This is going to be reg info and rs2 mask. And this one's going to be reg info and rs1 mask. It's going to be reg info and rs2 mask. Just like that. Nice and easy. So now we can do write back. So we have write back, and here we can go H word rd equals registers reg info. Should change that. So let's copy these just in case we need them. Where's our R-type instructions? So if we go to state handler, go to the top, we can go half word based masks, paste these in. So let's change this to underscore W, underscore W, underscore W. I'll change this to just RD mask. So these will be the word representations of our masks. And we'll make sure we didn't now just we did okay. So change these to underscore W. And then we'll change this to underscore W and remove the inst. Alright, so those are good. So now we'll make these the rs1 mask HW, so half word variation. And everything does stay the same between these in theory because they both represent the same order and the same bits. But what we're doing is we're just saying the joys of tabbing everything over is that once things start getting unaligned because you messed up, it gets to be a pain. So these are going to be the half-word variations for use with half-words and the full-word variations for use with full words. So we can say destination and RD mask half-word. Okay, so we have the register destination. We have the value to put in there. So now we go so we want define return flag HW. It's going to be 8 and then all zeros because that's going to be just the first bit set and nothing else. So this one we don't need to AND. Actually, we should still. Actually, what we can do is if reg info and return flag half word equals return flag half word, then registers, and let's see how we did it in our type, because I forget. So registers GPR RS1. Okay, so registers GPR RD equals value. So what this does is it takes 1, 0, and then all the way along, and it adds it to register info and checks if it equals 1, 0, 0, 0, dot, 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 dot. Because if register info has a 0 at the beginning, these will not be the same. If it has a 1 at the beginning, it will be the same. So that's our easy way to check, and then we write it into there. So now write back works. So now, if we were to go to, and this is getting a bit of a long video, but we'll add this last little bit in, and then that'll be it for today. We will go to logger.c, and we will create a, what is our log? Let's close all but this. Okay, so open this one, open logger.h. Let's create logging dump registers, and we'll go here, and we'll go void dump registers, and we can have a message if we want, but don't need it right now. F equals F open logger file path a F printf registers. I'll say dumping registers, new line, and then F close F, and then we'll print F, and we'll say tab, and which ones do we use? I'll just say rs1 %d, rs2 %d, rd %d, and we want, let's go to statehandler.c, convert them all to Unix line endings. I don't know why it asked me that after this time. We want to reg s registers, or reg info. So we forgot to add that there. S Alright, so we forgot to add those to those two. Alright, so let's look at what we're actually using here. We're using 1, 2, and 3. So 1's the destination. So let's go registers. Yes, we'll have to include that. Is it not included in DLX sim? It's not, okay. So we don't need it anywhere else, so we can just put it in there for now. So anyways, registers, GPR, we want, RS1 was 2, registers, GPR, 3, and registers, GPR, 1. So now if we do that, and we go to and we go to statemachine.c, and at the in-run state machine, if we process state, and then yeah, let's do a logging. Or how do I log in everywhere else? Logger dump registers. No. Okay. So now let's do that there and run. So this should be decode. Oh, where do we error out? Oh, I know what I forgot to do. Forgot to add dump registers. L dump registers equals dump registers, and then add dump registers up here. Void dump registers. Alright, so I forgot to do all that stuff. Alright, so now it should be fine. So now if we open up our logging file, which is going to be, it's going to be inside of our project. So let's find it really quick. Alright, there we go. Okay. So we got a lot of logging information here. But anyways, 10 and 11. So RS1 is 10, RS2 is 11. If we go to our source code, we'll note that in state handler, we set 10 and 11. So there we go. That's part of the way there. So let's actually, this is closed now. Let's edit this a little bit. So open up another text editor, and what we'll do is we will go to the bottom as soon as I'm actually allowed to edit it, because this is a big file apparently. Let's delete everything up to our new start. Yeah, this file is huge. Oh boy. It's a megabyte in size. So definitely printing out the executing of instructions is maybe not a good idea. We will change that. So let's do something else. Let's stop this just. Let's delete this log file. Oh, wrong interface. Let's delete this log file. Let's start again. Okay, so if we open up the log file now we'll have a much smaller one. State machine created, starting state machine, dumping the registers. Okay. So loop through again. Let's open this with an editor that'll update it. Notepad doesn't update it. Alright, so make this window a bit smaller. So it dumped the registers. For some reason it tabbed over dumping registers. Oh, that's okay. We'll look at that later. So, boom. Just printed out twice. They're still the same. Why do we error here? These are off. Oh, we need to shift these, that's why. This needs to be shifted 1, 2, 10, and this needs to be shifted 5. So define rs1 offset 10, define rs2 offset 5. So let's stop this again. rs1 offset. And that's just because otherwise we'll get a value that's too big for our to use as an index. So let's put these in brackets. So I'm pretty sure it's left to right, but I like to make sure that things are done in the order I want them to be done in. So then we'll do that, and go to the end, and then shift rs1 offset, and shift rs2 offset. And then if we go to state handler at the bottom where we do this, it's using rd, which is the last one, so that's okay. So let's run this again now. And look at our log file. So close that. Let's try this again. I want to open with Atom. Alright, I don't know why it's showing me everything there. I don't know why it's showing me Go stuff either. I don't need any of this right now. Thank you. Okay. So, 10, 11, boom. That's what we want. So let's step through. So now if we open up this editor, it dumped it twice. Now if we open it up, it should have dumped it a third time. And then fourth time. And then finally then right back the fifth time. 21, because 10 plus 11 is 21. So there we go. We now have our state machine actually executing an instruction all the way through the way it's supposed to. So now we can go to and we can start writing out something to read from a file and execute files that way. And then once that's done, we can start implementing stage 2, which will be our actual interpreter. And then when that's done, we get to start working on all the big instructions, loading from memory and accessing memory and all that fun stuff. But until then, that is something we'll do later. Quickly look at why this logger is printing out tabbed over. Oh yes, because we print a tab at the end. There we go. Perfect. So now if we were to run this again, just to make sure it's properly doing its thing, and then stop it. Definitely need to remove that printing of no operations. That's going to get big. So there we are. Just like that. We don't have no operation anymore, but we're dumping registers all the time. So we don't need to do that. So let's take out the dumping registers. So there we are. We now have a way to dump our registers. So we can use that if we come across an error where we need to, if we're processing an instruction and an error happens, we can dump the registers to see the register values, or we can even set this up to, instead of printing a file, we can have like an interface where we print these to interface all the time and we can see them changing as they change. But for now, it's just a way for us to print that out. So yeah, that's all for this video. We made a little bit of progress, and that we're now actually properly executing our instructions and are working through them like we want to. So at this point, we can start adding more instructions, and we can start working on processing files and get ever closer to actually finishing So until next time, happy programming.